Hello everyone, my name is MD Hasibul Hassan. Today I am going to present our study on comparative analysis of community level mobile source emission using big data analytics. First, I want to thank Metroplan Orlando for funding this study. Ozone is one of the 6 criteria air pollutant regulated under National Ambient Air Quality Standards. Unlike the other pollutants, other criteria air pollutants or hazardous air pollutants, ozone is a secondary air pollutant. That means ozone is formed in the air by the reaction of NOx and VO, nitrogen oxides and volatile organic compound in the presence of sunlight. So in order to control ozone in a particular region, it is important to control NOx and VOC. As you see here, Central Florida is in the verge of violating NAAQS ozone standard. Now, NAAQS ozone standard was used to be 75 parts per billion, but after 2015, it is more stringent now. It is now 70 parts per billion. So the design values of ozone in the regulatory monitoring stations in Central Florida is showing that the Central Florida is in the verge of violating ozone standard. So if it will be more stringent, it might gonna violate in the future, and it will be there will be expensive control policies coming from the federal government to the local government to control ozone. This is the source distribution of nitrogen oxides that is a precursor for ozone in Central Florida. We have 4 counties in Central Florida in this study: Orange, Osceola, Seminole, and Lake. So Orange County, in all the counties, as you see, motor vehicles is the dominant emission source of nitrogen oxides, followed by non-road vehicles like lawnmowers, leaf blowers, or construction equipment, and power plants for both 2011 and 2017. VOC emission is mostly dominated by natural sources, which is biogenic source, VOC emission coming from trees. But in Central Florida, man-made VOC sources, if you see, especially the urban counties like Orange and Seminole, motor vehicles is still a dominant man-made source of VOC, so that we can control with the policy that we have. Traffic has spatiotemporal heterogeneity. So to generate traffic-based emission inventory, it is important to gather accurate, detailed traffic information. So in this study, we have 2 methods to generate traffic informations and get the link level emission for all the roadway sections in Central Florida. First is state-of-the-art USCPS National Emission Inventory and Department of Transportation's sensor-based traffic dataset. Second is traffic data from crowdsourced mobility platform Streetlight, which is the data collection from Streetlight is from smartphone-based GPS. So we collected data for over 36,000 roadway links in this region using Streetlight data, and the vehicle ownership data are collected from Department of Motor Vehicles in this region, and meteorology data are collected from the airports in the 4 counties in Central Florida. Finally, motor vehicle emission simulator model EPS MOVES was used for link level emission estimation. This is the spatial distribution of emission from Streetlight model. As you see here, the green ones are low emissions and the red ones is the high emission. So the highest emission of NOx is around like over 100 tons. Our high emission of NOx are happening around Interstate I-4, Orlando downtown, and this Osceola Turnpike roads, and also in the peripheral highways of Central Florida. All the minor streets are showing very low emission using streetlight model in 2017. This is the right figure is the difference of the streetlight model emission and the US EPA's F dot related default and MOVE's default related emission. So as you see in the peripheral roads and the major interstate I-4 and Florida Turnpike, the street light is actually overestimated the emission. But in the minor streets, this MOVE's default emission that is backed up with F dot ADT is overestimating the emission, overestimating the NOx emission. So the green ones are street light overestimating, and the red ones are MOVE's default model is overestimating. Temporal distribution of emission in Orlando is showing high emission of NOx and VOC that are expected in daytime, especially in the morning and evening working rush hours in major highways. Street level roadways are not observed with high emission, even in daytime. The nighttime emission is low across the entire roadway network. Here is the annual emission estimation for VOC in the entire Central Florida, the link level. So similar to NOx, we see the annual VOC emission in 2017. The difference is the green ones is street lights is overestimating, the red one is street line is underestimating. So street line is estimating emission high at the major roadway sections of Central Florida, like Orlando downtown, I-4, and Florida Turnpike, and the peripheral highways. And the other minor streets is streetlight model is underestimating. So we have ADT difference between average daily traffic difference between the streetlight model and the F dot ADT. So as you say that the red ones means streetlight model is overestimating ADT, and the green one is streetlight model is underestimating ADT. As from the it's similar to the emission model, street line is overestimated the major roads, underestimated the minor roads. As a result, as the traffic pattern is following the emission pattern, which is expected as we are modeling the tailpipe exhaust. For temporal emission comparison, we choose three representative roadway sections. One is the downtown I-4, and second is the Florida Turnpike, and the last one is the local urban Michelle Hammock Road. Downtown I-4 is one of the busiest roadway sections with distinct morning and evening peak hour high emission for both street light and MOVE's default model. The left figure is the emission taking the entire roadway section of the downtown I-4, and then the right figure is the emission from in the middle of the section, middle link. So what do we see that if we consider the entire roadway section, like at the right, we have the street light is overestimating the emission. The street light, especially the rush hour emission, is much higher in interstate I-4, except like this one link where street light emission is lower than most default emission. Florida Turnpike section is a rural highway, mostly used by heavy-duty vehicles and high-speed traffic, where a working rush hour high emission is not observed. Rather, only one peak was observed at the middle of the day. Here, streetlight data overestimating emission for all the hours because there might be some inadequate or incomplete rural traffic sensor data that is not depicting the actual traffic condition in a rural region. Michel Hammock Road is an minor urban road that is located near UCF, but the traffic in this road is mostly generated by university activities. So we can see several emission peaks from a streetlight model, but for MOVE's default factor, we have only 2 peaks. The MOVE's default factors are modeling this road like a typical urban road that has 2 working hour peak. But here, streetlight emission is lower on the local road than MOVE's default emission. In conclusion, there are significant difference of traffic data between streetlight and f.adt, but in the future study of in the future of this research, we are going to investigate why there are some differences occurring, why the streetlight is providing higher emission and higher traffic in the major streets, and the it's underestimating the traffic and as a result underestimating emission in the minor streets. But our methodology can be implemented in any part of the United States to improve their mobile source inventory. Thank you for listening to my presentation. If you have any questions, feel free to email me here, and if you want to learn more about our research, please visit our website. Thank you.